Hello everybody and welcome to ES403 heat transfer. This example we're going to do an alternative to the lumped capacitance method, which is going to go take us clear through energy balance in order to find what the temperature of this sapphire rod is after it's been rapidly cooled and then had insulation wrapped around it. So these are the properties of the material that we're working with. A few of the assumptions. This is what we're looking at. We've got air flowing over it until time of 30 seconds. One thing to think about this is the fact that the rod is wrapped in insulation. So when you're working with the inside of it, you can pick almost anywhere inside, but certainly the center of it. So when we're grabbing equations, that's going to be important. Because since at T infinity, after 35 seconds, whatever the rod will uniformly become a single temperature all the way throughout, so you won't have to worry about any specific area of the rod when doing the analysis. So let's go ahead and jump right into this. Let me get myself organized. Okay, so first of all, I said we were going to do an alternate to the lumped capacitance, but how do we know that we can't use LCM? Well, in order to prove that you can't use lumped capacitance approximation, you have to find the bio number with respect to LC, since this is an infinite cylinder, we have LC is equal to R naught over 2. So if you do this calculation, you'll end up with H of 1600. I'm not going to put in the units. They were listed before. The numbers were listed before. Times ROH, which is 20 millimeters. I guess I'll put units here because you have to do this to do the calculation, which is 0.02 meters all over 2, all divided by K, which is equal to 22.3. And if you get that, it's equal to 0.72, which is not less than 0.1. It's not less than 0.1, so you can't use LCM. So LCM is no good because it has to be the bio number has to be less than 0.1 for LCM to be valid. So we're going to use a different system here. So what we're going to do is we're going to use the one-term approximation, which hopefully your professor has introduced to you, which is equal to theta star 0 equal to C1 exponential of negative zeta 1 squared times the Fourier number. Okay, so this is the equation we're using. Now, Fourier number is equal to alpha t over r naught squared, and in order to get C1 and zeta, we have to get the bio number. Now, here's something that's really important to remember. In this case, using this method with an infinite cylinder, bio number is not this equation. Bio number is equal to h r naught over k. So, in this case, we used R naught over 2 for LC, for this term right here, as you can see LC. But in this term, we're using directly the R naught, the distance from the center to the outside. You have to know this and know the variations of this for a sphere and a cylinder when you're using this alternate method. This is the equation you're using if you use the lumped capacitance method. These are the equations for bio number that you use when you're using this alternate method. You have to remember that. It's very important. Otherwise, you'll mess up the entire problem. So, if you do that, you'll end up with this equal to 1600 times 0.02 all over 22.3, which is equal to 1.43, which is the bio number that you'll use. And then you'll go into your table, and you'll find that C1 from this bio number, C1 is equal to 1.26, and then zeta is equal to 1.403. So we've got these two values now, right here. And then for the Fourier number, in order to do this calculation, I'm actually going to bring this back over here just real quick. Let me make sure I'm not telling any lies. Okay. Yeah, just a second. I gotta make sure I show you where the alpha came from. Okay. Well, you should be familiar with the equation for alpha, so I'm actually not going to show that just to save some time here. So if you find the Fourier number, you'll find that it is equal to alpha, which is equal to 5.2 1.29 times 10 to the negative 6 meters squared per second. All over, or no, times 35 seconds. Now you'll notice we're using 35 seconds. That's because that's the time when everything is kind of shut down. We don't care about everything that happened before then. We care about what's happening at 35 seconds. So that's why you pick that as a time. And then R over R naught, which is equal to 0.02 meters squared. And FO is going to be equal to 0.46. And in order to use this alternate method to make sure you're doing it right, Fourier number has to be greater than 0.2, and it is, so this is good. We can use it, and we can use this method. We can use this approximation equation. If this isn't correct, then you have to use the expanded version of this equation that includes sines and cosines and Bessel functions and all that good stuff. So it's great that we get to skip that part. So now, if we take this equation down here with the values that we all found, we'll find that theta star is equal to 1.26 exponential negative 1.40 squared times, square bracket there, times 0.46. And if you solve that out, it will equal 0.766. Okay, so now we have this theta star, which is actually equal to theta over theta I, if you want an explanation for that. So, we're still looking for the temperature at the center of the thing after a certain amount of time. Now, the way you have to do this, you might say, oh, well, we can use T and T infinity and so on and so forth. Turn this into T naught minus T infinity all over T initial minus T infinity. Well, no, you can't, because since this is for when there's a convective airflow over the outside or something like that. If you're comparing, these T infinities is not the same as temperature at time infinity. So these are not valid. This continuous relation. So what you have to do is do an energy balance. So E at infinity is equal to E at 35 seconds, something like that. You can set it up like that. So if you go ahead and set up that energy relation here, what you'll end up with is E in minus E out, just write this all out, is equal to delta E, which is storage, basically. Okay, and then if you go on with that, you can change this E storage into Q is equal to negative E of a time minus E original. And this equation should be in your book. You should have been introduced to this. So then Q, negative Q, is equal to E of T minus E of 0. So we're going to be using, we're going to be using this equation. And to do that, we have to have a Q of some kind. So we're going to go back into our book and grab yet another equation. This is really kind of tricky, so I apologize for that. But in order to use an energy balance, you have to have this in terms of energy. So what we're going to do is use the equation Q over Q naught is equal to 1 minus 2 theta star original, which is going to be this up here, all over zeta 1, Bessel function J1 of zeta 1. So I said we were going to have to use Bessel functions up here. Well, we have to use them here. And that's in a chart in the back of your book, so it shouldn't be that big of a deal. So if you fill this out, this theta and this theta, they're all from up here, so you still use this theta. You'll end up with this equaling 1 minus 2 times 0.766 all over 1.4036, and then J of that theta is going to equal 0.5425 from the table. So this is all going to equal 0.408. Okay, so we've got Q over Q now. So now, going back to our energy balance, this is what we're shooting for. If we look back in the section, you'll see another equation for Q's. I apologize for this. Well, no, using this equation, These can all be related kind of as how much energy can be stored. So what I'm going to do is change this to negative Q is equal to rho CV of T average of infinity minus T infinity. And this is the exterior temperature again from the airflow. So Q naught. Okay. So let's talk about this equation for a second. So this kind of jumped out of thin air, but it really didn't, because if you take energy stored, it's the change, how much energy it can hold right here, and how much it will have originally or after a certain amount of time. So this is the energy of the sphere as a certain amount of time goes by with relation to the exterior environment, and this is how much energy it can actually had originally. So it's kind of a step back from this, but if you think about it, the total energy that's stored in the cylinder is equal to the energy that it gains from the environment minus the energy that it had originally. That's basically how that is. So all the energies that ever were, or added, or came, or left, are the ones that you have to use in this equation. So if you use this, and if you say Q naught is equal to rho CV of T initial minus T infinity. This is T of infinity, this is T initial, so T times 0 basically. Minus infinity. If you put that in here, and then divide it all by Q naught so that you have it in relation to this, so I'm going to go ahead and do that. We've got Q over Q naught is equal to 0.408, which is then equal to T infinity. You go ahead and divide this whole side by this value right here. T infinity plus Ti minus T initial times 1 minus Q over Q naught. Okay, so here's an equation we can work with. Because this is all equal to T of infinity. So this is what we're looking at. So the temperature of the interior of the sphere at infinity is equal to basically the ratio of the original temperature, or the new storage, the total energy storage over the amount that's stored, which is equal to this that we calculated up here, which is equal to this equation, which is a relation of, again, that ratio that we found, the temperature of the outside and the temperature of the inside. At the time, 35 seconds. And the reason it's at the time 35 seconds is because of all the way back up here when we were calculating Fourier number, which we used in Q star, which gave us this, which is right here. This is in relation to 35 seconds. That's basically our original temperature. So that's how that all kind of came together as a synopsis. And if you go ahead and do that, you'll have T of infinity is equal to 300 Kelvin plus 800 minus 300 Kelvin times 1 minus 0.408, which is equal to T at time infinity after it's been heated up and insulation has been put on it, equal to 596 Kelvin. And that is your answer. That is the interior temperature of that sapphire rod at time equal to infinity after it's been exposed to temperature for 35 seconds. And that's how you do it. You set it up, you find everything at T 35 seconds, then you find the ratio of Q to Q naught at 35 seconds so that you can do an energy balance here. You finagle the energy balance a little bit so it's in relation to values that you still have, and then you solve it out and you get the temperature. It's kind of an artistic equation because you have to be able to see all that stuff, but it's not mathematically difficult.